So, when I was growing up, there was a program called Connections run by James Burke, and he would go through this list of things, starting somewhere really random and ending up at like jet engines or computing or something like that. And he showed the connections through history, how these things developed. Now, this particular story, what I'm going to talk about in the video, is worthy of James Burke. It's one of those really weird connections that you would never have imagined until you actually see the list of connections and think, oh yeah, it's about this. We made this wind turbine. It's super simple. It's a bit of cloth glued to a disc, and it was inspired by a number of things. One was the Persian designs, Nash Difan, and they're like 1,000 years old or something like that. But it was also the work of Simon Grippenberg, who's a Finnish artist, that put those two together. And while I was looking at this, I came across this wind turbine design. All those three things bunged together led to that design of turbine, which I thought was quite interesting all by itself, but that design of the disc with the rotating flaps has caused quite a lot of interest. Now, that design was done by a chap called Robert D. Hunt. Robert is in fact a doctor. He's a doctor of physics, and he worked in nuclear engineering. I think he's from Tennessee. Anyway, Dr. Hunt came up with that design, but it didn't spring from nowhere. Dr. Hunt's been really interested in aviation for ages, and he's the guy who's responsible for the gravity plane. Now, as far as I can work out, the gravity plane itself is a combination of a glider, an aeroplane, and a blimp. Essentially, you fill up the two pontoons with helium. It rises up through the air. When it gets to a certain height, you recompress the helium, and the whole thing drops to the earth like a rock. Now, that would scare the bejesus out of me, but it was a concept for a plane that was fuelless, in inverted commas. So as it's plummeting to the earth, what Robert decided to do was stick some turbines on there, some flat plate turbines. So the wind rushing over the plane would rotate those turbines and create the energy needed to recompress the gas. So that's where he came up with the idea. Now, he's been working in fluid dynamics for quite a long time, and he reckoned he came up with some things that were contradictory to the Bernoulli principle and some elements of drag. And he reckoned that the drag was the issue, because he said that he got this from watching oyster fishermen. The oyster fishermen would use lift to get out to where they wanted to be, then swing out a couple of boom arms and use drag to pull up the oysters from the oyster beds, because drag had more power, and so you could actually turn a greater torque using drag than you could lift. Now, if you're a physicist, don't argue with me. This is Dr. Hunt's idea. I'm just explaining it. Anyway, that's where he got this idea from the wind turbine, and then he went right ahead and patented it. Now, he patented it in 2004, so it's got a couple of years for the patent to run, and here's a patent. Now, the patent itself can just be pulled up by Google Patents if you want to pull that down, but it gives a good description of how he actually went about making that wind turbine. And of course, we have the demonstration. Now, it did go into field testing around about 2005 or so, and the gravity plane, of course, was the talk of the aviation industry at the turn of the new millennium. Now, they haven't progressed very far beyond that, and I don't really know why. I mean, one reason might be it's a whole load of bunkum. The other reason might be it's just plain scary to travel on a gravity plane, and I know from personal experience, getting things into production takes an awful lot longer than you think. It's actually quite an uphill struggle. So I'm not really sure why these things haven't gone much further than they have, because lurking inside of here is a whole bunch of really exciting things. One, Dr. Hunt's work on the Bernoulli principle. Two, this concept of drag and how drag can actually generate more than lift. That's going to really upset a lot of people. And three, the gravity plane itself. Now, Dr. Hunt was really keen to push across the idea that this was not free energy. It was not free energy because you used the motors to compress the helium, because you used helium to lift the plane, and the gravity return you got from the generation was to do with the fundamental force of gravity and the energy you put into compressing the gas. But there was a huge argument that that energy requirement was lower than the amount of energy you could generate from dropping this plane through the air. And that, of course, led to claims of over-unity from free energy. And Dr. Hunt was dogged by those for years, but it does raise that question, doesn't it? Because in one sense, of course, wind is free energy. I mean, we're not actually putting anything in there. We create a structure, stick it up in the wind, and when we look at that as an overall, where the energy from the wind comes from, then sure, it's not free energy. But if you look at it as the amount of effort you've put into building that machine, then you get excess energy out. So this is what Dr. Hunt was saying. It was about the scope of your view on the system that you were viewing, because he was using gravity. It was a gravity machine, really. And this over-unity aspect of it was not paying attention to the scope of the system that Dr. Hunt was using. However, he was dogged for a very long time about claims of over-unity. But the patents are still being allowed because, of course, the patents don't make that claim. But there's an idea in there that free energy within the scope of that system could exist by raising a balloon and dropping a weight, as simple as that. So whatever you think about all of these things, I thought that the connections there were certainly worthy of James Burke, and certainly there's a lot of interesting stuff in there for people to explore and to experiment with and to come up with improved design of your own. As you know, I particularly like this, not because of the amount of power it puts out, but because of the cost. It's so easy to make, so cheap to make, that the cost efficiency of a wind turbine like that, pretty much for whatever it's going to generate, is out of the ballpark. Very often people say to me, how do you get your ideas? And I don't really, so I'm going to give some credit. I try to give credit, but I'm going to deliberately do it now. A lot of what we're doing is based on Simon Grippenhook, who's the Finnish artist in residence, and from comments, because I basically have a look around, listen to what people tell me, see what's interesting, and give it a go. Of course, I'll try and make a few improvements, and it's a worry whether some of those improvements are actually improvements or not, but hey, you know, I'll give it a go, because what I'm interested in is accessible stuff we can do from things lying around us, and that's how I tend to bend things towards that, to see what I can do and how it can be made with just tools that every person's going to on average have. So that's the whole idea. But the ideas themselves are really just from looking around, reading, listening to what people tell me, and it was brought to my attention of the Persian turbines, which, to be brutally honest, 2 weeks ago I'd never heard about. They're in Nashtafan, which is actually in Iran. It's about 30 kilometers from the border with Afghanistan. And they're the oldest turbines in the world. And they're a kind of turbine called the Panamone style of turbine. It's a VAWT drag style turbine. Super interesting, super easy to construct. Now, in video 1547, we made this thing, and there'll be a link to that actually at the end of the video. There's a click link if you want to have a look at trying to build this. Dead simple, but follow that click link. And we're going to use this structure with a Panamone style drag turbine based on what the Persians were doing 1,000 years ago, which I think is awesome. Now, I did come across a chap who'd done exactly that, and he created this, which is essentially exactly what we're going to do, only this guy went for a patent, presumably because he put holes in the disc and that was worthy of a patent. He's now sitting at home daydreaming becoming a millionaire because Elon Musk will come and knock on his door, I imagine. Anyway, we're going to give that a go. We're going to give that a go with these LP records donated by Luke. Luke has a love of vinyl. I have no idea why, because I grew up with it and it's really scratchy, but this day and age folks love this, and this is from his collection, and apparently it got waterlogged, was sitting at the bottom of his wardrobe, and he's had no use for them at all, and so he donated them to us. And of course what we've got here is a perfect 12-inch disc. So we're going to use this to actually make our turbine with. Okay, to make this I've got my LP and I've got a bit of Tyvek. This is house wrap, although I imagine any bit of stiff cloth will do this, or even sheet plastic. Easiest thing to do, lay my disc on there, trimming knife blade, and then just go around it and cut out the circle. I got my circle, and then I drew 2 lines on it, 90 degrees apart, a bit of super glue on the reverse end, super glued it down. Then I took the trimming knife and cut a slice there, so it made this wing shape. Now let's shove that onto our axle. Ah, there it is together. 10 minutes work! Let's turn the hairdryer on it and see what happens. That's ridiculous! That works really well! So to make this generate, just glue some magnets on there and stick a coil underneath it. Of course, the very next thing you're going to want to do is a stack of them and see what kind of result you'll get out of that, but that was stunningly and stupidly easy to do, and apparently performs quite well actually. Well, certainly according to the guy who's trying to get the patent on them. So it really works quite well, dead easy to make, and we could do a whole stack of those. Now I used LPs because I had them, but any old disc will do. I was thinking cake stands, you can buy them for a few pence on eBay. CDs would probably make a wind wall kind of version if you wanted to go for something like that. There's a whole host of things you could do to make those discs, and if you really want a all singing, all dancing version, of course, you could do it in aluminium like the video I showed earlier. It may be surprising, but one of the biggest problems making wind turbines isn't actually the turbine structure itself. I mean, there's a whole host of things that you can construct that are being constructed from a couple of thousand years ago right up until now. There's just a huge range of them. One of the particular problems, and it's more special with VAWTs, is the bearing. There's all that structure goes down an axle and pushes on the ground bearing, and what you usually need is a thrust bearing. Now you can use a whole load of bearings for that. A thrust bearing itself is kind of a conical structure with some rollers in, but it's a mechanical bearing, so it's kind of expensive and kind of difficult to get hold of and kind of prone to breaking a bit. Now, some of the best bearings around are fluid bearings. Fluid bearings use a fluid between the two bearing surfaces, and of course that fluid can be oil, water, gas, whatever. And they split into two types, the hydrodynamic bearing and the hydrostatic bearing. The hydrodynamic bearing is where the fluid gets sucked into the space, because the spaces are so close fitting, and they force a pressure difference which raises one surface away from another, and you can see this in a glass syringe. Ground glass syringes are such good surfaces with a tiny area between them. If you start it spinning, it will continue to spin. It's quite amazing actually. These kind of gas bearings can also be bought, but they're in the region of $600 or so for a bearing. Hydrodynamic bearings is where the fluid is pumped in under pressure, and that pressure is maintained. Now fluid bearings have an awful lot going for them. They're virtually maintenance free. They're exceedingly low friction. They do have the friction of the fluids on the surface, but that friction is much lower than on a mechanical bearing, and they tend to be easy to look after. The only problem is they tend to be really quite expensive, but you can make a fluid thrust bearing all by yourself from simple materials you can find around, so I thought I'd go through that. What I've got here is a piece of pipe glued onto a piece of plastic, so it's basically a cup. And in that cup I can fit a bottle, an empty plastic bottle. On that plastic bottle I've put a rod. It's an 8mm diameter rod. When we drop that in there, then we have the basics of a thrust bearing, a fluid hydrostatic thrust bearing. All we have to do is fill that with water. Now, following Archimedes' principle on displacement, then this empty bottle will displace the fluid in there, displace the water. It will displace an equal mass of water. Now, of course, water has a 1 litre equals 1 kilogram, so we can look at it straight as being weight. This is a 500 millilitre bottle. If I were to fill this up, this would weigh 500 grams. Empty, what it means is if I tried to force it into there, I need to displace that 500 millilitres, or I need to displace 500 grams. So this bottle will successfully carry half a kilo just by dropping it in a piece of water. If I were to do that, I would have created a hydrostatic bearing, because it's going to wobble around like crazy because it's got nothing to support it here. So what I've got is a little hedge frame. This H-frame, there's a couple of bearings in it in the centre there. Those bearings don't support the weight, they don't support anything. All they do is when it tries to wobble, they nudge it back into a centre position. So these aren't contributing very much at all. There's a big reduction of friction of here because now it's being put on by water. So to demonstrate that, we're going to stick something on. What I've got is this fan blade. So we're going to put the fan blade on there and make our hydrostatic bearing. So I shoved my bottle through that fan and through this H support, and if I drop my bottle in there, we're pretty much ready to go. Now let's put some water in our pipe. As we put water in the pipe, we'll see that rise up a bit. It'll rise up a bit because the empty bottle is trying to displace that water, and it will displace the water to the mass of this and this put together. There she goes. We have reduced the friction on that incredibly, so even the slightest push with it will send that round. Put a hairdryer on it on low. So there you go, an incredibly cheap bearing that reduces the friction dramatically. So obviously where I've put the fan is where you'd put your structure, whatever your wind turbine structure is. This thrust bearing was the price of the pipe and some water. Its maintenance consists mostly of just topping up with water every now and then because nothing's going to happen to it. So I thought I would share that incredibly simple hydrostatic thrust bearing that can be used for making VAWT turbines to reduce the friction dramatically. Anyway, I hope you enjoyed the video. Thank you very much for watching, and please do remember to like and subscribe.